because diffraction is one more very important topic from wave optics from NEET perspective. Okay, so we know what is diffraction. It is nothing but bending of light around the corner of an obstacle or aperture. In fact, you would have seen the phenomenon of diffraction in your day-to-day life. Let's say that if there is a dark room, completely dark, and in the window you have a small hole, very tiny hole, and when light enters through that tiny hole, what happens? We see that like through that small hole, when light enters, instead of just seeing one bright light, inside we do see a region containing dark and light bands again. So there again inside the room we see at certain places it is bright, at certain places it is dark. Now this time the pattern that we see is not the same as interference pattern. In interference we see alternate dark and bright bands, and they it's like all the bright bands and the dark bands, they are equally spaced, but that is not the case in case of diffraction. In fact, diffraction also happens when we place an obstacle, like if you place a small opaque object. Now something like this. Let's say that you have a small opaque object here. Opaque object is one which doesn't allow light to pass through it. And let's say that you have some light source here from which light is coming out. So when light passes through this obstacle, obviously the obstacle doesn't allow light to pass through it. So obviously in front of this opaque object, there is no light. So basically you see shadow there because light is not able to reach that part. But exactly above this, because light can still enter like this, it can definitely pass through the corner of that obstacle. So on top of this shadow, we actually see this region which is illuminated, and this illuminated region has dark and light bands alternately. And this pattern that we see is called the diffraction pattern. So when we talk about the types of diffraction, there are two types. One is Fresnel diffraction and the second one is Fraunhofer diffraction. The difference is pretty simple. So when we are talking about a setup where the source of light and the screen on which we are observing the diffraction pattern, they are at finite distance from the slit. Like here you see, this is the source of light and this is the screen. And this one is the slit through which, like it's like everything is closed and you just have one slit which is open here, right? So this is the slit. Now here, if you see, the source is located at a finite distance from the slit. The screen is also located at a finite distance from the slit. That means the source and the screen, they are not very far away from each other. So this type of diffraction is called Fresnel diffraction. But when the source and the screen, they are far away from each other, like in this case, here again you have the slit and here you have the screen, and where do you have the source? The source is not seen on the screen, and that is why whenever you have the source located at an infinite position, then the ray of light coming from that infinite source is parallel rays of light. So these parallel rays of light are coming from some infinite source. So the source and the screen, they are like very far from each other. So this type of diffraction is Fraunhofer diffraction. Now you also see an interesting thing that in Fraunhofer diffraction you also have a lens. So why do we have this lens? That's because here, since the source is at infinity, so the rays of light which passes through the slit, they are parallel rays of light. So in order to make these parallel rays to focus on the screen, so what do we do to converge these rays? So we use a converging lens, which is nothing but a convex lens. And that is why we have used the convex lens, so that we can actually focus these parallel rays of light and actually get the diffraction pattern on the screen. So now we will discuss the Fraunhofer diffraction in more detail, because a lot of questions are asked from Fraunhofer diffraction in your NEET exams. Now, if you look at the screen, the diagram itself explains what happens in a Fraunhofer diffraction. So if you look at it, you see that the pattern that we get on the screen in a Fraunhofer diffraction looks somewhat like this. At the center, you have a maxima, which is called the central maxima, and it is very wide, right? And so this entire region is bright, and it is central maxima. And then we suddenly see that the intensity drops. So here you see the intensity has dropped considerably. So these points, like this point, these points are the secondary maxima. So these are secondary maxima. And we also come across points like this where the intensity is minimum. So these points are nothing but secondary minima. So now you understand the difference between the interference pattern and the diffraction pattern. In interference pattern, you have alternate bright and dark fringes. That's it. Here you have alternate bright and dark fringes, but here the intensity of the central maxima is very, very high. But the intensity of the secondary maxima is very less. So if you see, the intensity of the secondary maxima is very less when compared to the central maxima. Similarly, here the width of the central maxima is also quite a bit. Right? Now the question is, how do we find out the positions of the secondary maxima and the secondary minima? So let's first talk about the secondary maxima. So again, secondary maxima corresponds to the points where the intensity is more. So to find out such points, we make use of this expression which says yn is equal to n plus 1 by 2 lambda capital D by small d. And here the value of n could be 1, 2, 3, 4 and so on, because n cannot be 0, because n is equal to 0 corresponds to the central maxima, right? And here we are not talking about the central maxima. We are just talking about the secondary maxima. So for n is equal to 1, like you will have one secondary maxima for n is equal to 1. You will also have one secondary maxima for n is equal to minus 1 and so on. Now let's talk about secondary minima. So secondary minima, position of the points where we get secondary minima would be given by yn is equal to n lambda capital D by small d. Okay, another thing which I forgot to mention, capital D is nothing but distance of the screen from the slit. Small d is nothing but the width of the slit, and lambda is the wavelength of the light that is being used here. So the wavelength of this light which is falling on the slit. Okay. So in order to find out the secondary minima, again n can take values like 1, 2, 3 and so on. Right? So in this fashion, you can find out the positions of the secondary maxima and secondary minima. Now in case you come across questions where it talks about the angular position of secondary maxima or minima, in that case what do you do? So from the center of the slit, if you draw a line till the, let's say, secondary minima, this is the first secondary minima. So this angle theta gives you the angular position of the first secondary minima. Similarly, this angle gives you the angular position of the second secondary minima, or you can say secondary minima of second order. So corresponding to n is equal to 1, this is the first secondary minima. Corresponding to n is equal to 2, this is the second secondary minima or secondary minima of second order. Similarly, third order, fourth order and so on. And in this fashion, by knowing this theta, you can actually calculate the angular positions of the corresponding maxima and minima. Okay, now let's quickly focus on the central maxima. What if we want to find out the width of the central maxima? Because that's also interesting, because the central maxima is very wide. So how do we find out the width of the central maxima? So if you look at this, the width of the central maxima is basically this position. If you are able to find out the position of the first secondary minima and then just twice it, make it double, you actually get the width of the central maxima. Right, so 2y is the central maxima, where y is nothing but the position of the first secondary minima. And from here we already saw how do we find out first secondary minima, right? So for first secondary minima, you have to just put n is equal to 1. So y1 will be equal to lambda capital D by small d. So in this case, it is just, you are just making this y1 twice. So this is 2 lambda capital D by small d. Right, so this would be the width of the central maxima. So looking at this, you can see that the width of the central maxima is inversely proportional to small d. That means as the width of the slit increases, the width of the width of the central maxima will reduce. So if you have a bigger slit, then this central maxima will be less wide. It will be like small. And if you have a very, very small slit, like very small opening, in that case, the width of the central maxima will be very huge. And that is why when I took that example of a dark room having a small hole, in that case, your central maxima's width is so much that you actually see a huge illuminated region or a huge bright region, because that bright region is basically your central maxima, which is very, very wide. Yeah. So with this, we have very quickly revised the important topics of wave optics from a NEET perspective. Now, please do not rely on this recap. You definitely look at the video on wave optics of class 12 physics in detail so that you cover all the topics that